Yeah. So welcome everybody, and today's seminar would be given by Raju Vanugopalan. For most of the people here, he needs no introduction. So he is very well known for his work on the overoccupied limit on this. He's one of the actually pioneers of this plasma picture. And but today he's going to talk about a very interesting topic about how we can see a black hole in this plasma. So we are excited to hear about it. So over to you, Raju, then.
Okay, thank you very much for this kind invitation. So what I'm going to talk about is really somewhat provocative, but I hope you will see that it has some possibly some real teeth to it. And so I'm not going to be talking about ADS, CFT kind of duality, but really one that's based on QCD and Einstein gravity. Okay, so it's really four-dimensional kind of correspondence, which is kind of surprising and possibly has some universal features which are of general interest. So let me, okay. So what I'm going to talk about is an approach where I will start with QCD and I'll kind of develop a lot of the ideas in QCD, and then hopefully by the time I get to gravity, somehow these connections will start to be more manifest, and then that part will go a little faster, hopefully. And because the same sort of development that one sees in QCD in the high energy limit, you will also see on the gravity side, and that sort of makes these connections possibly more transparent. And the implications are things that are still being worked out, and hopefully can be put on a firmer footing, in the next years ahead. So I'm going to start with something, and I'm going to kind of take it slow and develop it. And so if you have any questions, don't hesitate to stop me and ask me as I go along. So you can hear me clearly, right? So it's fine.
Yeah, the audio is perfect.
Okay. So what I'm going to be talking about specifically is the computation of amplitudes in the Radial limit of QCD, and in particular, I'm going to be talking about the computation of amplitudes where you produce a large number of partons, or specifically gluons. So these are 2 to n amplitudes where n is large. So that's the physics of multi-particle production. And I'm going to be talking about this in perturbative QCD. And so the question one can pose is, how does one compute this? Okay, in first principles in QCD. And this is obviously of great interest because you can think of the LHC as a big 2 to n amplitude machine, right? So where you're producing copious amounts of partons, which then have very interesting dynamics. So the way to really compute things was pioneered by Lepada and his collaborators, and it goes under this name BFKL. That's Balitsky, Fadin, Kurev, and Lepada in the late 70s. And this was really a phenomenal tour de force piece of work at that time. And hopefully you'll get a sense as I go along why it was so. So if you start thinking about this and you write down this amplitude, you have 2 to n. And so they said, okay, let's think about this problem in something called, Ragikinematics, or specifically multi-Ragikinematics. And so there you have, you can draw the following amplitude where you have 2 partons, 2 gluons, with 4 momentum PA, PB, they scatter, and they go off into PA prime, PB prime, and they produce n gluons in the middle. And these gluons have momenta labeled transverse momenta KT1 to KTN, and then they have momentum fractions x1. So these are longitudinal momentum fractions x1 to xn, and there's a momentum transfer going between these legs from Q1 to Qn plus 1 all the way. So you can write down very simply the kinematics of these invariants. So there's the total energy, which is PA plus PB squared, and which is twice PA dot PB, right? The Lorentz scalar. And then for each of these rungs of this ladder, as you're going down, you can define the corresponding center mass energy for each of these rungs in terms of their, four momenta. Okay? And you can define these Ks as the momentum differences between one rung to the next. That's Qi minus 1. Now, what we call the multi-radial limit is the one where the total energy of the process, the 2 to n process, n plus 2, is much greater than the energy of each of the individual rungs, energy squared, we should say, which in turn is much greater than the momentum transferred going down these legs here. Further, the 4 momentum squared is such that it's just minus the transverse momentum squared, okay, in this kinematics. And these are so-called Surikov variables where Ki are written in terms of these numbers, alpha and beta, multiplying PA, PB, and simultaneous and plus K per pi. So this is the definition here. And then you can understand how you get this kind of relation here. Okay. And so S times the product of K1 perp is the product of these S's, and then these are transverse to the definition of transverse is that the dot product of this with the initial 4 momenta is 0. Alternately, you can express these in terms of the so-called rapidities, where Qi is K per pi e to the yi, or minus K per pi for the minus component times e to the minus yi minus 1, and then there's the transverse momentum. Okay? And Qi squared is basically the Mandelstam t variable going down each of these rungs. And in the multi-radial limit, this also corresponds to an ordering in these rapidities as you go from PA down to PB, where the rapidity is a log of these momentum fractions as you go down this ladder. So this is sort of just setting this up. So you can say, okay, now how do I actually compute this amplitude? And how do I compute it, just beyond tree level? Can I compute it over loops? And how do I organize the calculations in that case? So for that, let's just start thinking about just a single rung of the ladder and say, okay, let's look at first all the possible real emissions that I can get from this. So you have these two gluons coming in. As I mentioned, there's momentum transfer, say, Q1, Q2, down the rung of this 2 to 3 process here. So I'm just looking at one rung, 2 to 3. And then you see, oh, there's 3 possible ways I can emit gluons. And the remarkable thing, which was noticed by Lepada, was that you can sum up all these different emissions into one effective emission, okay, where the gluon is emitted from the center of this exchange here down this ladder. And this effective vortex, it's what's called the Lepada vertex, okay? So it's a non-local vertex. It depends on both the momenta that are being transferred down this ladder, but it's gauge invariant, okay? So you can write this whole thing in terms of a gauge invariant object, and it satisfies a Ward identity that this Ki that's being emitted dot C is 0. Okay? So then this 2 to 3 amplitude, this real amplitude, which is a function of the Mandelstam variables S and T, right, can be written as twice S, 1 over T1. So that's the transfer down this way here. That's the propagator. The effective vertex, C, right, which is non-local. And then this propagator T2 here. Okay, so that's the 2 to 3 vertex, which you then kind of resummed all these different contributions in just one rung of the ladder. Okay, so now you say, well, I know there are virtual corrections also. So let's again look at this, 2 to 2 part of the ladder and say, okay, what are the virtual corrections? So you have some momentum transfer K down this way, you have Q minus K down the other way. But then you also, of course, have this cross ladder that you can have. And so the sum of the two, it turns out, you can write down with this purple line here, where you can compute this, and you can write this 1 over T propagator with this virtual correction as 1 over T times log of S over minus T times an object we'll call alpha, where alpha is now log of minus T over mu squared. Okay, so there's an infrared cutoff in this diagram here, in this one loop diagram. So that's the effective propagator if you absorb these virtual corrections in something effective. So you go from 1 over t to 1 over t times log of s minus. So it's a double log contribution. Okay? So the other important part of this work that Lepada and collaborators came up with was this idea of Ragisation. Okay? And that's a very important concept that has extended into many areas of physics subsequently. And at its heart, it's this beautiful idea, which is now if you say, okay, let me now try and compute all possible loops, okay, for this 2-to-2 process. So then now for the one loop, I replace this by this purple line here, which is this logs. Now you say, okay, let me, in this kinematic limit that I'm working in, I can argue that it's the all loop contribution is just the iteration of these purple lines. Okay, so I have multiple loops which are corresponding to this. And of course, in reality, as you go to high loop order, it's much more complicated, but this is an ansatz, right? That you claim gives you the leading contribution to all orders in the virtual loops. And that's replacing now this purple line by this squiggly line here. So that's the so-called region. And the statement is that the propagator goes from 1 over t, okay, so this for a single run, to 1 over ti times e to the alpha. So you exponentiate these logs, okay, as you iterate them. And so it's e to the alpha ti times y minus yi minus 1 minus yi. So y, that's just log of, s over t, right, in the Radial limit. That's the rapidity. So this is the rapidity divergence here, and this is the infrared divergence. Okay. So this double log structure is nothing but, again, a word you hear in the literature, that's the Sudakov form factor, okay, which resums these kinds of double logs in the Mandelstam variable t and in s over t. But this has an infrared divergence. Okay, so when you compute cross-section, and if you were to take this infrared cutoff to 0, then the cross-section will just go to 0. Okay, so this 2-to-2 amplitude will just vanish if you were to take mu to 0. Now, as I mentioned, this Ragisation is an ansatz. Okay, it hasn't been proven to all orders, but it has been tested up to 2-loop order. Okay, there's a paper by Fadin already from 1998 where he shows that you can actually compute this Ragi trajectory alpha of t, right, which is this log up to order alpha s squared, 2 loops. And it's conjectured that this actually may break down at higher orders. Okay, so this is something that is a very active point of discussion in the literature about whether Ragisation can be shown to be valid to high orders, or at least formulated in such a way that it can be extended. So a parenthetical remark, which is not so parenthetical to a lot of people, is that to this 2-loop order, right, this Ragi trajectory can be obtained from what's sometimes called a cusp anomalous dimension. So you can reformulate this problem in terms of the anomalous dimensions of the product of vacuum Wilson loops. Okay. And this idea actually goes back all the way to Polyakov. So he had a 1979 paper called Gauge Fields Rings of Blue. And so basically you can think of this Wilson line as this kind of a loop in general, and then you have a little pinch on top that's a cusp. That's the anomalous dimension. And that anomalous dimension in the high energy limit is nothing but this object here that one can compute. Okay. So this Ragi trajectory, to summarize, can be obtained from the cusp anomalous dimension. And this program is called infrared factorization. So this was really developed quite a bit by Korczemski and collaborators early on, and now there's a large number of people working on this. And so people have computed these cusp anomalous dimensions now to 3 loops, actually. And that can then be used in principle in the Radial limit. So there's a nice paper by Korczemski and Korczemska who discuss this. Okay, so now I have talked about one run. I've talked about the real corrections with the Lepada vertex, which is gauge invariant. And now I have the Ragisation ansatz for this single loop log. So now I can put all these together and construct the full ladder, okay, of 2 to n reduction, not just 2 to 3. And basically the ladder consists now of effective vertices going all the way down, okay, and radii gluons in between them, okay? So in this way, I'm summing in this multi-radii kinematics all real and virtual corrections to all orders, okay, to this computation. And then if I combine them into a color singlet projection in this amplitude, that's what's called the BFKL Pomeron. And that's the amplitude. And if I take the imaginary part of this amplitude, that gives me the total cross-section in the limit that t goes to 0. Okay, so that's the total inclusive cross-section for 2 to n production. And so you can break it up, having understood this this one rung, excuse me, you can write it as a piece which is just color factor. So you're summing from n to infinity, where it could be this n being this being capital N, where you have a color factor times the coupling constant. Then you have all the phase space factors, right, from each of the rungs. So it's a product of all the phase space factors. And then you have a product of these propagators. So you have a propagator 1 over t from the amplitude, 1 over t prime from the complex conjugate amplitude. And then you have this virtual correction, right? You replace 1 over t by this factor. And so you get this factor of the rapidity divergence times this infrared radii trajectory from both sides of the rung, this side and the other side. And then you have the product of the two Lepada vertices, C mu times C mu. So this is this gauge invariant non-local vertex. That's it. So having understood this one rung, you can construct the entire rung for 2 to n production to all orders in perturbation theory with this kind of structure here. Okay, so this is kind of the heart of it. So it's, of course, it still looks extremely complicated. And so the way you solve for this is that you first take, you go to Mellon space, or you go to angular momentum space. So you take a Laplace transform where f of L can be thought of as the Laplace transform of this object here. And then that then simplifies in such a way that you see that the Laplace transform has a form which is L minus 1 minus alpha times T1 minus alpha T2. So this is your famous radii trajectory, and that's why this alpha can be thought of as the as the radii trajectory corresponding to this these loop corrections here. Okay, so now you've connected this classic idea of radii trajectories to that of infrared divergence in the computation of an amplitude. Okay, so that's kind of a very nice thing that was already found by them, and that's why it's called this radialization ansatz. Okay, so that's the connection there. So now defining f in some terms of some Fourier transform, you can then obtain this result in terms of that Fourier object as a so-called as an integral equation. Okay, so this integral equation is the BFKL integral equation, and this can be solved. Okay, it's fairly straightforwardly. So you can solve this integral equation for this radii trajectory, and that's what gives you the BFKL equation. And then you can do the inverse Laplace transform to obtain the 2 to n amplitude. Okay, and when you do that, you do the inverse Laplace transform, you can see that the total cross section, which is twice the imaginary part of this guy at t equal to 0, can be written as s to some power lambda. Okay, where this lambda comes from this alpha, from this radii trajectory, and it has a number. You can calculate this. Okay, it's 4 alpha SNC or pi log 2, and it's 0.5 for some fixed alpha s value. So there's a few things to note about this, which is that even though the radii trajectory and radialization absorbed all these virtual corrections, so there was a divergence in this radii trajectory. You find when you compute the BFKL Pomeron, the real and virtual corrections cancel. Okay, so instead of double logs in the result, you only have single logs, and the single log is just that of the rapidity. Okay, and that's something for a finite energy is not divergent, right? It only diverges when you go to infinite energies. So this is a very important point, is that this double, so there's a lot of discussion in literature about double logs and so on, and it turns out when you compute something that's this color singlet combination, it kind of cancels. The other thing is that this gives you a strong violation of the Froissart bound. Okay, so the growth of the cross section is much more rapid than you would expect from the log squared that you get from the Froissart bound. So you can now, of course, do go even beyond what's called a leading logarithmic approximation in which this was computed, this multi-radial kinematics. And people have done that. And so the NLO BFKL equation has been known for 20 years now. And after a lot of further work by Gavin Salam and collaborators and so on, resumming various contributions, you find that this lambda is more like 0.3, okay, than instead of this. So it's square root of s. If this is a power squared of s, then lambda would be 0.3. Sorry, as opposed to 1 for the case of square root of s. So it's still a rapid growth, but that's what you get from perturbation theory. So now when you start doing this, so what's the conclusion is that when you compute 2 to n amplitudes, the rate, the cross section for this 2 to n amplitude grows very rapidly with energy. So as you go to higher and higher energies, it's easier to produce lots of soft partons. Okay? And at some point, the density of soft partons becomes so large, the phase space density, that in addition to just this ladder contribution, you start to have these split ladders that you can have, which are naively higher twist in the usual perturbative QCD language. They start to become just as important as these simple ladder contributions. Okay, and you can have things
Raju?
like where yeah.
Sorry for interrupting. There was a question written by Sujay Ashok. He's a string theorist at IMSC.
Sure.
Who works on gauge theory. So he's asking basically, some diagrams were neglected in this Ragisation ansatz, and is it possible to elaborate some regime in which one can assume that this ansatz is the most dominant contribution?
Yes, so that's the regime, as I mentioned, where the energy is very large. So it's really in the Radial limit where the energy is very large and the momentum transfer is small. So this is sometimes called low X physics. And so then what you're doing, and I didn't have a chance to go through in detail, is that you're summing what are called leading logs in X. So there's you systematically compute, logs that come with so it's higher order contributions that come with logs of X. So where alpha log X is of order 1. And so when alpha log X is order 1, you can organize the series in such a way where this Ragisation is the dominant contribution. And you can compute sub-leading corrections to this. So resumming all orders of alpha S times alpha log X to the N and so on. So there's an organization as what I call leading log in X, next to leading log in X, and so on, which will organize this kind of series as you go to high energies.
So Raju, in this context, this ordering of rapidity is the thing that gives a dominant contribution also. Without the ordering, it is important to figure out this dominant.
That's right. So as you go down the rungs of the ladder, the assumption is that the rapidities are ordered, but the transverse momenta are all roughly the same. Okay, as you go down this ladder. And so that allows you to resum systematically these logs of X order by order. So,
and Raju, can you comment whether these kind of answers can be tested further in n is equal to 4 superangles, where you have more dualities like between amplitudes and Wilson loops, for example?
Yeah, so I mean, so for example, the BFKL equation is also being derived in n equal to 4. And in some ways, I believe it's an easier derivation. So one of the things I should mention is that the BFKL equation is conformally invariant. So its kernel has this Mobius invariance, which was noticed very early on. And you can use conformal invariance as part of the solution as well. And in n equal to 4, of course, as you mentioned, it's in some ways a simpler derivation to derive the BFKL equation. But the answer is yes. So that is the form of the 2 to n amplitude in n equal to 4 as well. There's a BFKL equation for
that. Thank you.
Okay. So but now we have this issue that I mentioned, that is, you can have these kinds of, recombination higher twist contributions. And another way of saying it is that the operator product expansion that we know as a tool in perturbative QCD really breaks down when you get to these high parton densities. And so, as I mentioned, you can have these recombination type things where you cut the ladder in the middle of this fan diagram here, which is like a recombination kind of contribution where two soft gluons combine to form a harder gluon, if you like, at each rung. So that's kind of breaking this ordering in a way in softness. And then you can have such kind of screening contributions where you cut one or both of the legs of the fan. And these are naively higher twist. They're suppressed by powers of q squared. But because the number of gluons is growing very rapidly, that's compensated in the numerator by the large number, okay? So in the Radial limit where q squared is fixed, but x is going to 0, such contributions become as large as the leading contribution, okay? And so there's a competition between the growth, the Bremsstrahlung of soft gluons, which is very rapid as you go to high energies, and the recombination of softer gluons into harder gluons. And there's a state of maximal occupancy that's reached, okay? So if you plot the boost, like going to higher and higher energies, on the y-axis and the resolution scale, which is q squared, on the x-axis, for any fixed resolution q with which the probe probes inside the hadron. As you go to sufficiently high boosts, this object becomes very dense. Okay. It reaches maximal phase space occupancy of 1 over alpha s. Okay. So you can have a smaller resolution scale. It'll happen much quicker, right? Because these blobs are bigger. So they will saturate phase space much quicker, but that's true at arbitrarily large q squared. As you go up in energy, this thing will become dense at some scale here. And so where q saturates, right, where this for each q, there's a value of x at which you reach maximal occupancy. And that emergent scale is what's called a saturation scale, okay? So it's a dynamical scale, which is a function of x. So for each q, there's an x at which you reach unitarization, okay? You reach maximal occupancy. And that occupancy is 1 over alpha s, okay, on the saturation line. So if you define maximal occupancy as 1 over alpha s, you get this emergent scale. And it turns out, as I will discuss, that this scale is also the scale at which the theory unitarizes, okay? You have perturbative unitarization. So even if you are in the UV with very large q squared, if you go to sufficiently high energies, the theory will become, highly occupied, okay? So a very strongly interacting theory at very high occupancies. And so this is this idea of classicalization that you get, you can think of these highly occupied partons as classical fields satisfying Yang-Mills equations, okay, as you go to sufficiently high energies. And so you see from perturbation theory, from first principles with Ragisation and so on, you get this kind of result that you have very high occupancies, which are then characterized by an emergent scale, which is this saturation scale. And there's an EFT in which you can understand this picture of how this occurs, and that's what's called the color glass condensate. And the basic idea is the following. So if you have a non-perturbative distribution of classical sources, so imagine you're going down the rungs of the ladder and you think of all the partons in the higher rungs above the rung you're interested in as being some distribution of sources, which, because you have a large number of them, live in some higher dimensional representation of your algebra. And so because of that, they're also classical, okay, because they live in this higher dimensional representations. Those colors commute, okay. So given this, and then you have a distribution of them, and these then couple to the glue in the lower rungs of your ladder, okay. And so given this such a distribution coupled to over-occupied background glue, you can compute quantum fluctuations in that small window. And then you can systematically, as you go down the rung, absorb these quantum fluctuations into the sources as you go down the rung, okay? And that iteration is nothing but the renormalization group. There's a self-similarity there, okay? And so the idea is that you start with some cross-section, which is some distribution of classical sources. You can write it as a path integral because it's classical. And there's a weight functional for that with the cross-section in the presence of these sources. So you're computing amplitudes now in the presence of the source, right? So I'm computing now the 2 to 2 amplitude, where now I have the other n-2 guys are sources for this production here. Okay. And so now you can do quantum fluctuations, and these quantum fluctuations to this amplitude can be absorbed in a renormalization of this weight functional. And this is the renormalization group that one gets, and that's sometimes called the Jim-Wilk renormalization group, which I'll talk about in a bit. Now, the thing that occurs when you do this, right, is that, you know, propagators, right? So you can resum all these contributions into propagators, right? Where you can write down you can define effective propagators, which is just a bare propagator plus all possible insertions from these classical sources on say a quark line, which is defined by some free propagator times this effective vertex times the free propagator again. Okay, and similarly for a gluon, you can write this as a free gluon times an effective vertex times another free gluon as this way here. Now these effective vertices can be rewritten in modern language as a Fourier transform of Wilson lines. Okay, so for the quark, there's a Wilson line in the fundamental representation, and for gluons, there's an analogous one in the adjoint. And this Wilson line is nothing but a path-ordered exponential of all these sources that correspond to the higher orders of the higher rungs of the ladder. So the point is that imagine you're computing some quark loop, which is now dressed by all these sources, right, which are at large x for both sides. And so these sources then are of order 1 over g. They are very highly occupied. They're classical sources. So you can have arbitrarily many of them, and they can be represented in terms of Wilson lines in the high energy limit. Okay, and so they include all this coherent multiple scattering, if you like, of all these sources to all orders in rho over transverse momentum squared. Now, a parenthetical remark here is that these effective vertices for quarks and gluons are nothing but, in Lepada's framework, what are called quark-quark region and gluon-gluon region effective vertices. Okay, so it was also realized in somehow this stringy community by Simon Carr and Huot that you can sort of think about, you know, regions in this language of Wilson lines. But you know, this was kind of prefigured, as I mentioned, in the work of Korczewski, but also there were papers by Lepada and collaborators who make this connection very clear. Okay, so in this CGC EFT, what appears right away when you do like a one-loop computation in the presence of sources, right, can be understood in this old region EFT language as quark-quark region vertices. So regions are, again, as I mentioned, this object which now you'll recognize look like these multi-loop kind of insertions, right? So if I sew these rows together, then it's like producing these multi-gluon loops. And so that's kind of this interesting thing that you obtain immediately in the semi-classical EFT picture. So now I'm going to go through with you a very simple example where you see kind of the power of this EFT. Okay, so imagine you're at the LHC and you, yeah.
Raju, sorry, can I ask what is the precise connection between this region vertex and the Wilson line in general? I mean, it seems that you are making a statement that this computation can be understood as the Wilson line computation.
Right. So what I'm saying is that each of these rows, right, can be thought of in some sense as these radii as gluons, if you like. Okay, and so you're going in some ways beyond just the usual radialization. But if you think of each of these rows, and then you sew together two rows, right, and you compute when you compute a cross section, then that's like constructing a loop. Okay, so that's kind of this connection with this virtual diagram that I mentioned. This this region diagram. And so, for example, but when you compute something like the BFKL equation, then you're computing some color singlet combination of these rows, and that's That's how you get the BFKL equation. But the remarkable thing is that when you do this one loop computation, you'll see immediately now, as I'm going to go through this example, hopefully where it'll become clear that you see this kind of Wilson line structure as you go along. Okay.
Thanks.
So, yeah. But the way to understand it is that what you're doing is that if you solve, this is a semi-classical picture. So if you do compute the quark propagator in the background field of gluons, right, then it turns out that the solution is this Wilson line. And there's a nice physical interpretation of this in terms of color memory that I will come to briefly, a little bit later in my talk.
Hi, Raju. These are all light, like Wilson lines.
Yes. Right? So in this particular case, so this is what. So let me go through it in this slide, and I'll address that point. Your question is very apropos, because when you think about the original Krochemsky picture in terms of cusp anomalous dimensions and so on, that's more for more general trajectories. So a cusp is basically just an angle between incoming and outgoing line, which emits a gluon. Okay, so that's that angle here, and you can think of that angle as a rapidity, if you like. And so, but in the high energy limit, of course, these are like Wilson lines. So in that sense, it's kind of simpler, right? But the idea of cusp anomalous dimensions is more general, this is really, the high energy limit is a simplification in terms of these infinite or semi-infinite Wilson lines. And so that I will illustrate in this very simple example. So think of you have a quark, which is very forward at the LHC. So you're measuring it very forward, fragments into a jet. And as it interacts with the other hadron, it scatters strongly. Okay. Now the other hadron, that multiple scattering of the hadron can be represented by this effective vertex, right? And this has a Wilson line in it. And this is in the amplitude. So this quark is at some spatial position x perp. The anti-quark in the complex conjugate amplitude is at a position y perp, right? And so the cross section is just in the product of amplitude times complex conjugate amplitude. And then you get a trace over the product of Wilson lines at two different spatial positions. So as Sayantan asked, right, these are really light-like Wilson lines. So the idea is that you have a loop, right? It's a light-like loop, but you start at x minus of minus infinity, you go to x minus plus infinity, down to x perp from y perp, and then back again. Okay, so this is this light-like Wilson loop. And this is an object which is called a dipole. Such dipoles are the building blocks of high energy QCD. So it's not parton distributions in the high energy limit, which are the building blocks, but it's these dipole objects, which are the fundamental objects. And there are other such objects that I'll come to in a second. So this is a classical computation, right? It's leading order. But now assume that I have the emission of a gluon. Okay, so I have now both multiple scattering due to all these rows that I mentioned, right? Plus now I have this emission here. So again, if I have this ordering in rapidities, x1, x2, x3, right, then all of these soft Bremsstrahlung contributions, right, can be absorbed in the RG evolution of this dipole, okay? So I have this, what's called an impact factor at some x, and then I have evolution here. So I can compute corrections to this object and corrections below. And these corrections below can be absorbed into this Wilson line, right? So in other words, if I have such an object, the dipole, which I represent as S, as at some rapidity here, and then I emit the soft gluon, then at the next rapidity, right, I get the same kind of dipole, except now the connection between these two can be represented as an RG equation. Okay, so the change in this S, right, this S matrix, as a trace of two Wilson lines with rapidity can be written as a kernel, right, which is the BFKL kernel, times S minus SS, okay? So what you now see is that because I included all these multiple scattering contributions to all orders in rho, I have these nonlinear terms as well. Okay. So this picture of both Bremsstrahlung and multiple scattering, right, is where you go beyond BFKL, because BFKL doesn't include these multiple insertions, okay, from at each rung of the ladder. It only includes one insertion. But when you include all possible insertions, you get such nonlinear terms. Okay? And this is the essence of the physics of what you sometimes hear called shadowing. Okay, so you have screening that occurs, and this screening is captured by this equation. And this is the famous Belsky-Kupchagov equation.
But Raju, one thing can I ask?
Sure.
So to get this picture right, we need this strict ordering in this rapidities. So as far as I understand, okay, in this in this particular diagram, it was probably obvious, but when you more complicate by emitting horizontal things as well as vertical things, is it obvious that this kind of ordering will be the dominant contributions?
So in the high energy limit, right? You can organize things in such a way where those will appear as sub. So this is what is called a leading logarithmic approximation, and so then they will be the next to leading log approximation, and so on. Okay? And in principle, if you include, all next to leading kind of approximation, then you've included all possible contributions at some order in that expansion. So then you can understand the mapping to other limits of QCD. So for example, the BFKL equation maps onto so-called DGLAP at high Q squared. Okay, so the high Q squared limit of the BFKL equation, you recover the DGLAP double log equation. So not the full DGLAP equation, but DGLAP at small x. And then you can do this kind of matching order by order. And so in fact, you can use the BFKL anomalous dimensions at some order to extract DGLAP anomalous dimensions to all orders, okay, or to some very high order. So this kind of matching can occur, okay, as you go along. So this is some systematic organization of graphs in QCD, where now the new feature is that you're also including all possible twist contributions as well. So you're simultaneously doing an expansion in alpha S, but you're doing an all twist expansion at each order as well. Okay, and that makes sense in this dense limit where the occupancies are very large. So you start from that limit and then you work backwards, if you like, to low densities. Yeah. So this BK equation, this Belsky-Kupchagov equation, you can show the structure here. Right, it has two fixed points, okay, to this equation. So one fixed point is at very low densities, but the other is when the parton density is very large. Okay, so in other words, when the scattering, the S matrix basically goes to zero, okay, where the survival probability of the parton goes to zero. And that's sometimes called a black disk limit in the literature. And this occurs precisely when the occupancy is of order 1 over alpha S. Okay? So when you reach this maximal occupancy, and in fact, you can define in this dipole picture the maximal occupancy as a size of this Wilson loop of order 1 over QS. Right, so that's kind of the scale in this area law, if you like, or flight-like Wilson loops. Then you find that this cross-section unitarizes. Okay, so this tells you that you get perturbative unitarization of amplitudes at high parton densities right away. Okay. The other limit is this dilute regime, where if you expand around S equal to 1, that it's very weak scattering. Right, to lowest order in these sources, you obtain the BFKL equation. Okay? So this very complicated equation that I went through the derivation for you, where you construct these rungs and you match real and virtual. There's a bootstrapping that you do. There's a bootstrap between real and virtual contribution. then and you get the BFKL equation. In this semi-classical picture, it just kind of falls off the page. Okay, so in basically a few pages, you can just derive the BFKL equation, and that's just the low density limit of this very dense kind of multiple scattering picture that one has. Okay. So now you can look at more complicated. So the power of this approach is that you can look at arbitrarily complicated or interesting, depending on your perspective, processes. So suppose you have, say, PA scattering at the LHC where you produce two jets. You produce a quark jet and a gluon jet, and then you produce a bunch of other soft stuff, right? So that would correspond to a quark coming along. It splits into a quark and a gluon at two different spatial positions in the amplitude, two different rapidities, and likewise in the complex conjugate amplitude. Okay. So this cross section turns out, because you have both now, if you look at these blobs, there's a quark-quark region and the gluon-gluon region vertex. So this has a fundamental Wilson line. This has an adjoint Wilson line. So when you take the product, you get products of 4 Wilson lines. Okay? And these tell you that there are new objects which are not just dipole configurations, but you have novel quadrupole-like configurations of Wilson lines. Okay? And so such contributions, right, they include all possible Bremsstrahlung and multiple scattering contributions. Okay, so you're including all of these contributions, and that's what's the equations that describe not just dipoles but also quadrupoles are called the Jim-Wilk renormalization group equations. Okay, and in principle, depending on the complexity of the process, you can look at 3 jets, 4 jets, and so on. You have a whole hierarchy of such non-trivial topological structures, right, of Wilson lines, and this hierarchy can be solved by one equation, okay, which is called the Jim-Wilk renormalization group equations. Okay, so again, to leading log accuracy, these equations describe an entire hierarchy of endpoint correlators that describe such complex processes. Okay? Now, unfortunately, and this comes to Ayan's question, this leading log resummation is not good enough for precision studies. So there are 2 kinds of corrections. One is, if you have a separation in rapidity between what is the projectile and the target, and this object is something sometimes in the literature of ray physics called the impact factor, and this is the evolution, right? So there's a kind of OPE in rapidity between the projectile and the target. So if you look at more and more complicated processes, right? So say 2 jets, 3 jets, and so on, and then you dress them. So these dressings don't come with logs in X, okay? So they are not in rapidity. They are all in one unit in rapidity. Then you can also compute this systematically. So like in perturbative QCD, this is like computing a coefficient function to higher and higher orders. While the evolution can also be computed to higher and higher next to leading log X and so on. So this part, the claim is universal, right? You can use it in deep elastic scattering or in hadron-hadron scattering. But the part that's above here is non-universal. It depends on the final state that you look at, right? That's a coefficient function, that's process dependent. And the state of the art right now in this field is that this stuff has been computed to next to leading log accuracy. So people have gone beyond this leading log resummation, and that's sometimes called NLO Jim-Wilk. Okay, and then this part people are just starting to compute. Okay, this non-universal part for different processes, people have started computing them. Okay, so for example, I've done something along these lines for DIS with my collaborators, and there are lots of calculations going on in the literature. Okay, so this program is still not complete. You know, so Simon Kahren-Huot, for example, has made really a fantastic progress in really computing parts of this evolution to next to leading log. Okay, using conformal invariance, he's been able to extract information on that next order. So now I come to somehow moving towards the second part of my talk. But before I go there, I want to mention that this question of amplitudes, especially soft amplitudes, has aroused a lot of interest. And when you think about things like these cusp anomalous dimensions and so on, they have a different kind of interpretation that has been advanced in terms of so-called asymptotic BMS-like symmetries. These are Bondi, Weinberg, Metzner, Sachs-like symmetries, which are originally discussed in the case of gravity at null infinity. And basically, the idea is that you have these symmetries correspond to a group of conserved charges. Okay? And these are conserved charges that live on each point of a celestial sphere at null infinity. So this is a two-dimensional stereographic projection of the transverse plane. At each point, you have conserved charges, and then you can understand the behavior of soft emissions in terms of conservation laws that these charges satisfy with the S matrix. And it's been shown by Strominger and his collaborators that such symmetries are equivalent to a formulation of for QED of Lowe's theorem, which tells you that there's a factorization between soft factors and hard amplitudes. And the claim is that you can show that the conservation of such charges with the S matrix shows that you can write this in such a way that these soft photon clouds are infrared finite. Okay, and that it comes by absorbing so-called collinear divergences that you get in QED, right, into these clouds of soft photons that you have that dress these electrons in QED that are scattering of each other. So another way of saying it is that you redefine your S matrix in such a way that by absorbing collinear divergences in the usual way of computing S matrices into the initial state as coherent states, you get a finite S matrix at the end of the day. Okay, so this whole program is sometimes called Faddeev-Coolidge, goes back to their original work in 1970, and this is again an issue of active investigation in the field. Okay. And now this also apparently works for QCD. So there's been quite a bit of work suggesting that these soft gluons that dress hard amplitudes, one can argue that at null infinity, right, they satisfy a conformal 2D current algebra of these conserved charges, of which there are an infinity of them on the celestial sphere. Now, this is all kind of academic for QCD, unless you can argue that Yang-Mills, there's a regime of scattering where Yang-Mills is appropriate to think about. Okay, and that's precisely the CGC regime of high occupancies, because there you have this emergent scale, right, which is QS, the saturation scale, which is large in the radial limit. And this weak coupling scale allows you to apply all these ideas about soft gluons and asymptotic symmetries in a regime of QCD amplitudes. Okay. And so then the interesting question is, how do we understand, all of the CGC stuff that I'm talking about in the language of these, of these infinite dimensional symmetries in the celestial sphere, and whether you can reinterpret such CGC states as Faddeev-Coolidge type coherent states in QCD. Okay, in other words, the S matrix is not the asymptotic S matrix of free quarks and gluons, but of these CGC states, which are then just colliding and producing these N gluons. Okay. So in this CGC picture, if you compute the classical fields in the presence of sources of these gluons that are being produced, right, then it turns out that there's a remarkable solution where it's a shockwave solution, where you think of this hadrons as being boosted to the speed of light, the highly Lorentz contracted x minus equal to 0, and then essentially these infinite dimensional symmetries correspond to each point on this transverse plane where the vacuum on one side of the shockwave is separated from the vacuum on the other side by a large gauge transformation. Okay, and it's discontinuous. So in traversing, if you have a probe that traverses the vacuum from one side of the shockwave to the other, okay, it does so by it gets a kick in the process and emits soft gluons. So you can think about each of these guys as being sort of these, multiple vacua in which corresponding to large gauge transformations at each spatial point in the celestial sphere. And then when you make a transition, you emit soft gluons. So this is kind of exactly analogous to the picture that Strominger and collaborators had in the context of gravity and QED. And this is one realization of it in the high energy limit. So these Wilson lines and these quark-quark region and gluon-gluon region propagators are precisely the color memory effect. And these correspond in this picture to color rotation and kick that's experienced by a quark-antiquark pair that traverses this hadron shock wave at high energies. And so you can actually show that the solutions are identical in the two cases in the high energy limit. And so you can really think about this traversal of a probe as a kind of, this is the Wilson loop that I was talking about, okay, or VV dagger, right, at two different spatial positions. And so you can think about a flux is going through this. So you can ask me this question that all these BMS symmetries are at null infinity, right? What does that have to do at some finite x plus that you're talking about? It's finite time. And the remarkable thing about these solutions is that they're independent of x plus. So you can really move them to x plus equal to infinity in a high energy limit. And so that's equally valid either at finite x plus or at null infinity. Okay, so that's kind of the exact correspondence that one has in the two cases. So now let me come to this other issue that I was talking about, which is gravity. I'm kind of running a little bit late. So where one can think about 2 to n amplitudes in the radial limit of gravity. Okay? Now, this connection between all the stuff that I was talking about in the context of QCD and gravity was prefigured in a remarkable paper by Lepada in 1991, where what he did was he constructed an effective action which describes high energy processes in QCD and in gravity, where the intermediate particles, gluons and gravitons, have this multi-radial kinematics that I went through with you in the first slide. Okay? And he constructed the S matrix, and he wrote this in terms of correlation functions for two field theories where you have a separation between longitudinal and transverse two-dimensional field theories. And this program was then continued and continues with the work of Amati, Ciafaloni, and Veneziano. So they wrote a whole series of papers where they developed gravitational scattering, so 2 to n gravitational scattering, in this multi-radial language of Lepada, and using the multi-radial techniques that I described to you in the context of QCD in terms of Lepada vertices and Ragisation and the like. Now, at the same time, in parallel, roughly, there was a paper by Lenny Susskind, where this is a paper which has over 3,000 citations, and I checked, actually, it's his most cited paper. So this is really kind of a blockbuster paper, where he's now talking about, the motivation is black hole formation and the information loss paradox, and it's all about weak partons. Okay, what happens to weak partons at high energies when your Lorentz contract, when they kind of infall into a black hole? So when you have this 2 to n process, what is really happening to weak partons? And he then argues that all the information then is contained in the horizon, and that's what gives you an error law and so on, in terms of Bekenstein's principle. And he also, I should mention, he also acknowledges discussions with Lepada on high energy scattering in this paper here. And I think what is interesting is that none of these papers discuss parton saturation. Okay, so if you read through Suskind's paper and his discussion of light front coordinates and small x and so on, it's all about it, but there's no discussion at all of this high occupancy that can be formed. And I think that qualitatively changes the picture of how one thinks about this problem, and that's what I will come to shortly. Now, implicitly in Lepada's work are the ideas of parton saturation, and his work can be actually connected to ours on the CGC through this one-to-one map where we understand our color sources in terms of his quark-quark region or gluon-gluon region propagators. Okay, so there's this map that one can do. So it's implicit in his work. Oops, sorry. So now what is the real connection there between these? And this actually is a very old idea, even though Lepada's work actually predates this work of Kawai, Lewell, and Tai. And that's based on an observation of the relations between closed, kind of Shapiro-Virasoro type amplitudes and open Veneziano type string amplitudes. And the connection is in the low energy limit can be represented as a relation between Einstein and Yang-Mills amplitudes. Okay, so in other words, the tree level cross section in gravity, in Einstein gravity, for say this 2-2 process, can be written as essentially the product of the tree level Yang-Mills amplitudes. Okay, so it's kind of a square. So you can think in this limit of gravity as a square of QCD. And then there was an explosion of interest and following an observation, a remarkable one, by Bern, Carrasco, and Janssen, BCJ, where they argued that if you compute in QCD this object here, the amplitude for tree level gluon-gluon amplitude, in a kinematics where the external legs are on shell, you can write down this tree level amplitude as a product of kinematic factors that's n sub s in the S channel times the color factors in the S channel divided by S. And likewise for the T and U channels, the Mandelstam variables. You can write down this in this very nice way here, where the color factor is given by this, and then you have some kinematic factor in terms of the polarization tensors and the four momenta in this 2-2 process. So what they showed is that the tree level gravity amplitude can be obtained by replacing these color factors by the same kinematic factors for that process. So Ci goes to Ni, okay, G goes to K or kappa or 2, and you recover this tree level gravity amplitude. Okay? So this is shown explicitly for the tree level amplitudes, and there's a lot of work ongoing to extend this to loop amplitudes, and there's a nice review by Bern and collaborators in this direction. However, as I mentioned, this work was actually in the radial limit, was prefigured by Lepada already in 1982. Okay, and for a more modern Spinner-Helsty kind of derivation, there's a more recent paper you can look at, where he argued that the 2 to n amplitude in gravity can be written just like in QCD, where you have some impact factor at the top and bottom of the ladder. So that's the process dependent stuff. And then you have these Lepada propagators, right? This T channel things, times the Lepada vertex for gravity. Okay. So you have this effective vertex going down the ladder at each rung of the ladder. And this effective vertex is nothing but a double copy of the Lepada vertex in QCD. Okay, so it's a product of two of these gauge invariant Lepada vertices, and likewise the QED Bremsstrahlung vertex here in the second term here, it's a square of that. Okay, and this is kind of remarkable because that was something in 1982 was extremely surprising that you could really think of constructing a gravitational amplitude in this way. Now you can rewrite this as a color kinematics duality as well, but it's much more tricky. And is discussed in this paper by Johansson, Sabivera, Campillo, and Vasquez Mozo. Now, so what does that mean? That this double copy between QCD and gravity amplitudes in the radial limit suggests that in gravity, this 2 to n amplitude grows much more rapidly than the QCD amplitude, and in principle, one can compute it. Okay? And that was done by Amati, Ciafaloni, and Veneziano explicitly in several cases. Now, just as I argued to you that in QCD, when the occupancy becomes 1 over alpha, the system unitarizes by forming this classical state. Likewise, one can argue that when n is 1 over alpha gravity, this dense graviton state unitarizes to form a black hole. And this is something that was argued by Duali and collaborators in a large number of papers. And further, this has a remarkable implication that this black hole picture of gravitons as highly occupied self-bound states is UV complete. Okay, so it unitarizes the cross section by itself without need for further UV physics, and this is because of this classicalization, this high occupancy, which is already at a weak coupling scale. Okay, and so in this picture, gravitons, okay, on this boundary have wavelengths, component wavelengths, which is on the order of the Schwarzschild radius, okay, which is given by square root of n, where n is this occupancy times the Planck length. So it's a much larger scale than the Planck length. And the gravitational coupling defined as is the Planck length over the component wavelength of the graviton, which for RS is 1 over n. And when n goes to infinity, this coupling goes to 0. Okay, so it's a very weakly coupled, highly occupied limit of the theory. The claim is that the theory unitarizes perturbatively these 2 to n amplitudes already at this scale, right? And so you can.
Sorry, Raju, can I ask something?
Yeah. Sure.
So in the case of QCD, we had the saturation line, which was dynamical scale, which was x dependent, right? And so here, is there any analog of that? Because
it's the exact analog of that. So the idea is that how things look in terms of really depends on the scale at which you probe them. Okay, so the coupling really varies with this component wavelength, right? So so the maximal occupancy that you have, just like in the CGC case, is this kind of scale, which in turn depends on the occupancy. So for different occupancies, you have different values of this scale. Okay, the only criterion is that this n is of order 1 over alpha. So for different wavelengths, you're going to have different n's at which this condition is saturated. Okay, so this picture that you fill up a box with partons of all the same size is completely wrong in this picture, as it is, we would argue, in the QCD picture. So if you have this, if you read a lot of black hole papers, they talk about, okay, you're trying to fill up this box with these partons, and then how does the box grow? And the statement is that the box self-organizes by producing effectively partons of smaller and smaller size in such a way that you don't have to change the size of the box. Okay, so it's kind of this self-regulation due to screening that you have in the box, and it's the same thing that happens. I will come to this correspondence in more detail in a slide or two. But within this picture, what they showed is you can just think about the black hole evaporation rate as really the leaking of these gravitons from this bound state. Okay, so the gap that these gravitons have is also 1 over n. Okay, and so the classical geometrical picture of black holes is only recovered when n goes to infinity strictly. Okay, where this horizon is then exact. Okay, that's Hawking's semi-classical picture. But for any finite n, you have this weakly coupled gap state, and then you can compute the black hole evaporation rate in terms of the 2-to-2 scattering of gravitons in this object here. And then at high occupancies, that rate is again just 1 over the Schwarzschild radius. Okay? And you can compute for the Hawking temperature, which is h over rs, which goes as 1 over square root of n. You get all the familiar expressions for the expressions for the half-life and the lifetime of the black hole, which then scales as n cubed times the Planck length. So when n goes to infinity again, the black hole becomes infinitely long-lived. But for any finite n, it's a metastable state, that quantum state that one produces. So in this picture, you can also ask, what is the entropy bound? And there, in this context, the entropy bound is given as given by Bekenstein and proven by Cassini as having a maximum, which is 2 pi the energy times the radius divided by h bar, where this energy is the energy in some critically packed volume, okay, of the Schwarzschild radius of quanta. And you can show that the energy is then, in this case, just n times qs. So this would be q sub s. And the radius is at maximal occupancy is r sub s. Okay, and if you plug in these numbers, then you find that the Bekenstein entropy is 1 over alpha gravity. Okay. And so from a previous discussion, 1 over alpha gravity is just rs squared or the Planck length squared, and then you recover this familiar kind of expression that one has, okay, for the Hawkinstein-Bekenstein bound. Now, this entropy, however, much more fundamentally at some level, can also be expressed in terms of a Goldstone decay constant corresponding to the spontaneous breaking of Poincare invariance by the graviton condensate. So essentially, what you're doing is you're producing a classical object, right, in this process, and there's a decay constant for this object. And that decay constant, again, can be shown to be n times qs squared. Okay? And so if you can re-express the entropy in these units, again, as an area law of area times f squared. Now, the remarkable thing, or the conjecture, is that at n equal to 1 over alpha gravity, the saturation of black hole states also leads to unitarization. Okay? And so the way you see it is that if you just compute, say, a 2 to n amplitude, so the claim is that naively, the 2 to n amplitude will have n and n factorial because these are bosons that one produces. And then there's a suppression of alpha gravity to the n because you have, n such gluons being produced. But the claim is that there's also the degeneracy of microstates that one has that when in this 2 to n scattering, and that's given by E2S Bekenstein. So if you use the Stirling formula to approximate this first part, you can write that as n to the n e to the minus n, but then alpha gravity goes as 1 over n to the power n. Okay, and so you're still left with the suppression. So naively, you think that producing such a classical state in gravity is highly suppressed. But if n goes as 1 over alpha and the number of black hole states goes as 1 over alpha gravity, these cancel to give you a number of order 1. Okay, so the suppression in the production of such classical states is compensated by the degeneracy of these microstates. Okay, now, of course, if you go away from this critical point, right, of n equal to 1 over alpha, the cross section for black hole formation drops exponentially. So it's really only at this critical point that you actually have this process. So how do we connect this language?
Can I ask something? So the thing that is showed, this e to the power SPH, that seems to be like a non-perturbative contribution.
So it actually turns out, and let me come to this point, I'm going to address this point right now, is that actually not, because if you think about this in this Lepada language of 2 to n processes, this entropy factor can be directly related to the physics of BFKL in terms of the cancellation of real and virtual infrared divergences. Okay, so in other words, if you compute, say, loop corrections and real corrections, so what Dwali and company did is that they computed a tree level process, right? And then they argued that there's an entropy factor for these microstates corresponding to this process, which is this, and then they got this number, right? Now, what Veneziano and collaborators showed in this paper is that they can recover exactly the same result, right? Where you understand this as a factor that's arising from the cancellation of these infrared divergences in the pseudo-conform form factor with the real soft contributions. This is just like my argument in the case of BFKL, right? You exponentiate these infrared divergences in the pseudo-conform form factor, and then when you compute a cross-section, you find that these infrared divergences cancel, and then they give you something which is just like a rapidity factor there. Okay. And this is precisely the same object. And this again points to a deep connection of the exponentiation of these. So in gravity, this is nothing but Weinberg's theorem, okay? So this exponentiation in this language can be understood precisely in terms of Weinberg's soft graviton theorem. Okay? And that is discussed in this very nice paper by Adazzi, Bianchi, and Veneziano. So they're able to make a map of this language to that semi-classical language of duality. In precisely the same way that the BFKL language of amplitudes can be mapped to the semi-classical picture of the CGC. Okay, so there's a one-to-one map. It's just how you formulate the problem in the two cases, but the result is exactly the same. So this then gives you a glimpse of the elements now of the CGC black hole and portrait correspondence, where you can now use this to understand that you can think about where you can map a region RS equal to 1 over QS, right? Where QS is the saturation scale of the CGC, which can be mapped onto a black hole of analogous radius. And this scale is a weak coupling scale in both theories. So in the black hole and portrait, 1 over QS is square root of n times the inverse Planck length. So it's really a weak coupling scale, right? Where gravity is still weak. In the CGC, QS is square root of n times lambda QCD. Okay, so again, the scale is much larger than the confining dynamics that occurs at lambda QCD in the radial limit. It's determined by maximal occupancy of 1 over alpha, and that's where perturbative unitarization occurs. Okay, so you don't need to go to the regime of true strong coupling in either theory to have unitarization of cross sections, and it's energy dependent, right? So the weirder the parton, the quicker it saturates. Now, the correspondence between the two theories only occurs at this critical point, Q equal to QS, where the physics is universal, okay? It doesn't depend on the details of the dynamics of the weak partons in both theories. Now, the existence of this double copy between the two theories suggests that one can extend this double copy in amplitudes in terms of constructing, 2 to n amplitudes to a classical double copy between gluon and gravitational shock waves. Okay, so the picture of the black hole portrait and the CGC may have a quantitative correspondence. In principle, that's something we're working on, which is then also an active area of literature. And there's a nice review by Chris White that you can take a look at. So in fact, one can use this correspondence to conjecture what the Bekenstein entropy of the CGC is. And the arguments there go through in exactly the same way as in the black hole and portrait, where the CGC energy in a domain of size 1 over QS is n times QS. And so the CGC entropy is nothing as bound as 1 over alpha S. So inside a confining radius of the proton, which is 1 over lambda QCD, there can be QS squared over lambda squared domains, right? So the S of the proton is n times that of the CGC. So you have these n CGC domains inside the proton, and that's just 1 over alpha S squared, okay? Now, in a rapidity interval of size y, you can have 1 over alpha S V partons, okay? Because that's what the leading log result tells you, right? And so the change in the entropy of the proton with rapidity is just 1 over alpha S. Okay, so this is a formula one can derive exactly from this correspondence. And there's been a number of other discussions in the literature from different perspectives. It's a little hard for me to tease out what their answer is actually, but this is our prediction for what the entropy of the proton is, which is 1 over alpha S through this correspondence. One can also understand this entropy in the language of a decay constant, characterizing the breaking Poincare symmetry. So this BK equation leads to a kind of solitonic structure of this dipole wave function in momentum space, where the peak is given by the saturation scale, and it's a kind of traveling wavefront of the soliton, which moves outward with higher energies. And this spontaneously breaks Poincare invariance. Okay, so you have this solitonic state. And this is also characterized by a scale that's related to shadowing in QCD that I mentioned. And so this
Raju, can I ask something?
Yeah, sure.
What exactly do you mean by the entropy of a proton?
Well, I mean, so this is now in this case, I'm talking about in high energy scattering. So of course the the proton is a pure state, of course, right? And the entropy is 0. So what I'm really talking about is the entanglement entropy that one would measure in high energy. So if you were to break the proton into 2 pieces, right, and you were to try and ask what is the entanglement entropy of this proton, then this is the answer that you would get.
Yes, so are you kind of breaking it in rapidity space? Like you're saying that if you add
exactly. So if you look in some domains of rapidity, right, and then you ask what is the change in the entropy as I change my window in rapidity. So what I'm saying is that imagine that you have a proton and you are asking what is its entanglement entropy in a certain region in rapidity. Okay. And this is what the answer would be, is that the change in the entanglement entropy with rapidity is 1 over alpha s. So it has a meaning only in that context. Now, you can also think about it in the context of, say, high energy scattering of these 2 protons, and then the entropy they will produce in that process. And that can be tied also to this entanglement entropy picture that one has.
And then this alpha s is at the saturation scale QS corresponding to the rapidity?
That's right, exactly. So the QS is to determine it's a boosted confining scale. So right. So this physics is all about boosts and looking in some resolution and window and rapidity. Okay. And so the idea is that just like Susskind had this idea of these infalling gravitons or partons as getting boosted to higher and higher energies as they get closer to the horizon, then all the information gets packed around the horizon. And then the part that he missed out was you create this high occupancy state with an emergent scale that regulates the distribution of matter on this horizon. And so essentially, but the essential picture is right, is that you get an area law, okay, in this case, and the scale that sets this area law is this Goldstone decay constant corresponding to the breaking of Poincare invariance, okay? And so essentially these partons really screen each other, okay, on a surface that's this pancake, okay, at the horizon of the black hole. And that is, so you can write down this 1 over alpha s entanglement entropy as an area times f squared, where area is 4 pi r s squared. Okay? So if you are aware, I mean, the strict definition of the Bekenstein entropy, as shown by Cassini, was in the language of entanglement entropy, okay? That you can really derive this Bekenstein bound, and that's the interpretation that one has. In this case. So I've gone way over my time. I really apologize. So let me just end with some final remarks that this CGC black hole correspondence we outlined also extends to the evolution of the matter that we have produced. And there's a correspondence between how this CGC evolves in this plasma state, in a high energy scattering and black hole evaporation through Hawking radiation. The analogy, however, breaks down when the occupancies become a order 1. Okay, so in the CGC, there's a quantum breaking time where the occupancies become order 1, and that's when the CGC evolves to form a quark-gluon plasma. And at that point, this exact analogy kind of breaks down. And so, as I mentioned, the study of soft factors in the CGC and the relation to cusp anomalous dimensions is really a deep connection, which has to also can be reformulated in terms of this Fadia-Coolidge kind of language of coherent states. And this is something that we're also exploring in a kind of whirl-line QFT formalism of radiation from semi-classical whirl lines. This work in collaboration with Javi Fiel and Andrei Tarasov. And also there's this classical double copy of CGC and saturated graviton states to have a more quantitative understanding of this correspondence is also something that I'm working on. And this is in collaboration with Himanshu Raj, who's a postdoc at the Weizmann Institute and will be moving to Saclay this fall. So thank you very much for listening, and I'll be happy to take any questions if there are any.
Okay, thanks, Raju. It was really a very great talk, and really it didn't feel like it took an extra time.
Sorry.
So let's we are very engrossed. So let's have some questions.
Yeah, I have a very nice question. Can I?
Oh, hi, Santan.
Hi. Thanks for this very interesting talk. So I was wondering, when we have this black hole picture, we have like very quantum-based picture. Like people use number
Yes.
theory to calculate all these occupation states in a quantum system. How do you merge these two pictures? Like here it is like kind of a highly occupied system going into this black hole picture. So how do you reconcile these two pictures simultaneously?
Yeah, so that's a very good question. So I mean, so there's this classical picture, which is classical in every sense of the word, of black holes as classical objects, semi-classical objects, a la Hawking, and that is the limit where the occupancy n that I mentioned goes to infinity. So you can take a semi-classical limit where alpha gravity goes to 0, n goes to infinity, but Rs, which is the Schwarzschild radius, is a constant. So in that classical limit, you recover this kind of standard, geometrical picture of black holes. But for any finite n, just like as you know from for large n QCD and so on, you can really think about these as gapped states, okay, where the size of the gap is order 1 over n. So it's really, so the quantum nature is visible for any given n. And in some sense, this is also tied to this question of the information loss problem, because the statement is that if n goes to infinity in this picture, then it will take an infinite amount of time to recover the information that has fallen into the black hole. Okay, but at any finite n, you can compute the corresponding page time, which is this n to the 3/2 that I mentioned, in which you can kind of recover all the information that went to the black hole in terms of quantum states. I don't know if this addressed your question, but I'm happy to iterate.
Yeah, no, it's fine. And yeah, it's a nice thing when I need to read more about it. And I had another very nice question. So when I have this Balitsky-Kovchekov equation, so for that, is it is the CGC state or this the line of unitarization that comes as a fixed point of those equations, or how do you see the line of unitarization?
Yes, you can really see it as a so it's not just you can actually derive it. So it's essentially the QS is defined as the value at which this equation has a fixed point. So it's this nonlinear equation, and so it has an infrared fixed point at which the dipole cross section saturates, or the S matrix, and that condition is what actually gives you the scale. And so it's an emergent scale, so you can define the QS as lambda times some boost factor. So because you have some initial condition, right, for the Balitsky-Kovchekov equation. That initial condition contains the non-perturbative physics, which is scale of order lambda QCD, right? And so you find then that the unitarization condition gives you this emergent scale, which is a boosted scale of lambda times e to the some little kappa times rapidity. And this kappa is what you compute in perturbation theory. And that's what you compute a la BFKL or, all this Ray physics. And that you can compute systematically order by order. So what is remarkable to me, sorry, go on.
Yeah. No, I was also wondering, so you only showed the second order corrections to this decay equation. So the dipole term and the corrections to it. So there can be other higher order terms, but are they subleading, or does they change this unitarization line significantly? Or
no.
is there,
Well, I mean, so at the next to leading log, one still gets the same kind of one gets the same structure.
Okay.
And so, okay, whether this persists to all orders, we don't really know. But I mean, yeah, and again, this is deeply tied to this issue of the validity of Ragization. Because, because in terms of, you can think of these rows, these sources in which you compute these amplitudes, when you can think about it in terms of, say, back reaction to these sources, that could become important at high orders, and that could break this picture.
Okay, but no one has calculated the higher order corrections to this.
So as I mentioned, there's a remarkable paper by Simon Carn-Hewitt where he actually computed the next to leading log BK equation. And he computed, he didn't compute the full thing, including all the running coupling corrections and so on, but he included really kind of a significant part of the computation of this. And it's interesting, he computed this using kind of a space-like time-like correspondence between the space-like evolution of gluons and the time-like evolution of so-called non-global logs in jet physics. And he was able to use that to guess what the structure of the next to leading log BK equation is.
Okay.
And his computation, by the way, wasn't n equal to 4.
N equal to 4 super young.
Yep.
Okay. And in QCD, no one is doing this right now.
Well, that's something that I would like to do. so if you want to join me.
Yeah, that was very interesting.
So I think it's actually doable. And so we have invented some techniques recently in terms of these effective propagators, this gluon region, which make it very efficient to do high order computations, where you also resum all these multiple scattering contributions in these effective vertices. And I think then it is no more conceptually challenging than a 2-loop computation in QCD. And in certain kinematics, you can probably do it. And I think it's very feasible.
Thanks a lot.
Yeah. But I'm getting to be an old man, so I need some help. So it's in doing it, but I think it's definitely doable.
But you have a lot of nice ideas.
So Raju, I actually have something in between a comment and a question. So
okay. Sure.
So suppose this hypothesis of classicalization is valid in gravity.
Right.
And you also have some kind of emergence scale. So I would suppose that you could talk about corrections to Einstein's equations. And why it is important, because once you know how the equations are corrected, you can also compute corrections to the entropy. Wald has a formula for it. But now the entropy should be coming out from other considerations, because since you have a quantum picture here, so one can actually try to check whether the Wald entropy formula is valid now in this way of thinking. And that's exactly sometimes how string theory verifies goes about. So in string theory, you have corrections to Einstein's gravity, and we have this corrections which Wald tells us to incorporate to Bekenstein formula. So that is sort of a macroscopic side. And on the microscopic side, you can also compute the degeneracy in an independent way, and you match the both. And that's how you can go beyond Wittgenstein-Hawking and check the consistency of string theory. So I think that there is similar consistency check that one can perhaps do here.
Yeah, so I mean, can you understand this in terms of say renormalization of Newton's constant? So in other words, I mean, the structure of the expression is still the same, is that you still get an area law, but then you're renormalizing Newton's constant, right?
Well, no, because in the string theory picture, these are like quantum gravity corrections and not the stringy corrections, which are simply modifying that. So now, if you want to understand what is how this modifies the entropy, sometimes you can probably get it in a better way. The leading log term can be obtained, but I think beyond that, it is one has to go through Ashok Sen's quantum entropy function or something like that. So it is much more complicated, I guess. But if you just have classicalization, then perhaps maybe there is another way to
yeah. So I mean, the way I would think about it is that, yeah, so I think about the stringy aspect as a kind of regulator, just like in QCD, you think of the lattice as a regulator. And so you have a regulator, and then in principle, of course, you have corrections that depend on the regulator, right? And then so in the low energy limit, if you like, then you're insensitive to the details of the regulator. But then as you go to say higher energies, then you become more sensitive to those details, right? And then the picture could potentially break down. I mean, the part that's
but the main point,
the part that's non-trivial though is that, I mean, this structure by itself, unitarizes the cross section, right? So one has to somehow argue that there's a piece of Hilbert space that's somehow missed, in somehow in these considerations, right? Because the argument is that the Hilbert space is completely saturated by these states. And so it's in that sense UV complete. So the argument is that the theory is itself UV complete. I mean, that's the difference with QCD in that sense, right? So that there's that the UV physics kind of decouples in that sense.
Yes,
but so the only way it can appear is through renormalization of the coefficients that you have.
Yeah, I understand. I think, of course, yeah, you can similarly think probably of. I have no better way to say. But
I mean, this is a kind of RG picture. So basically, the statement is that it's non-Wilsonian in gravity. While in QCD, of course, it's Wilsonian because
the kind of corrections I was talking about is you have some regulator scale and you have basically 1/RS, that energy scale, and there'll be a large ratio of this too. So you have some kind of UV regulator, right? And that you need anyway in gravity, right? Because gravity without a UV regulator would be catastrophic. So in some sense, one can perhaps introduce some sort of these effects into the picture.
I agree. So yeah, so systematically you can compute these UV regulation effects, right? And yeah. But yeah, so the question is, do they do more than normalize the Newton's constant? That's the question.
Okay, I understand. Because you don't have a natural way of producing some sort of natural higher curvature effects or higher derivative effects here in this case.
I mean, the statement is that this really saturates the Bekenstein bound, right? So
yeah, then actually we also we actually created recently some model, which is actually in the other regime, perhaps, where the black hole is small. And so we had a microstate model, which is very reminiscent of this CGC-like picture. So there we talked about fragmentation of the horizon into some throats, two-dimensional throats. And these are the analogs of the flux tubes. And then we had some soft gravitational radiation. So that was an unfragmented throat that was acting as sources for the flux tubes. And we showed that this model is remarkably beautiful because you can do information mirroring here. Normally we can't say how the information is being decoded and being coming out, but here we could actually answer this question. And so it is quite reminiscent of it. And so I don't know, I mean,
very interesting.
Perhaps a part of this picture could go on even in the non-perturbative regime in a way, but it's very interesting what you were saying. Yeah. There is some interpolation now to the perturbative limit.
Yeah, I'll take a look. Yeah, so I think these papers by Veneziano and collaborators are also very interesting because they also try to probe these boundaries in terms of where, in these amplitudes, where you see the effects of these, stringy scales as well, in terms of quantitative corrections to this picture. So they have some work along those lines, which I need to understand better also.
Okay, thanks. Do you have more questions? Okay, it seems like everybody is
just a few brave souls left. Yes, I know. So
I'm pretty sure a lot of people are going to follow once we put it on YouTube. And so good. I'm very happy, Raju, that you agreed to give this talk. Thanks for your time, and we really enjoyed this talk. And thank you for giving your time again. And
thank you very much for this nice discussion, and good to see you guys, and hope to see you in person before too long.
Yeah, sure, definitely.
Yes,
definitely.
Okay, next year.
Hope to see you in Chennai. Yeah.
Right, next year.
Yes.
So hopefully. Okay, so take care, guys. Thank you very much.
Okay.
Okay.
Thank you.
Bye.
Okay.
Goodbye.
Thank you very much. Bye.
I have to stop.